This lecture is going to be about electron energy levels and photons. Before we talk about electron energy levels, it's going to be really important to understand what negative energy means. We've experienced objects that have positive energy. For example, this 5 kilogram bowling ball would have some positive gravitational potential energy, and we know this because it's above some height that we're considering to be a 0 point of height. That position on the ground is where we're saying the bowling ball has a height of 0. So we can imagine that the bowling ball is, say, 8 meters above that 0 position, and we can use the gravitational potential energy equation to find that the total gravitational potential energy there is 392 joules. The important idea here is that that positive energy is defined compared to some 0 point where the ball has 0 height and so 0 energy. So if we were to just drop this ball on the ground, at that exact point it would have 0 potential energy because the height in the equation is 0, and so the whole thing is just 0. So we can understand positive energy and we can understand 0 energy. I want you to imagine now that we dug a hole in the ground and allowed a bowling ball to fall into it. And we can say that this hole is 4 meters deep in the ground. So it would be meaningful to say that this height is negative 4 meters. It's 4 meters below the place that we've defined to be 0 height. And if we plug a negative height into our energy equation, I can see that I get a negative energy as a result. This is negative 196 joules. Does it mean anything that that energy is negative? Does that tell us anything meaningful about the object? I'm going to say here that negative energy does mean something, and it means something unique from positive energy. Because if this ball has negative 196 joules of gravitational potential energy, I can see that if I add 196 joules to this ball, what that means is that the ball is going to be raised to the point where it has 0 potential energy. So negative energy can tell us exactly how much energy needs to be added to get an object back to the normal 0 energy state. You can think about it as being the amount of energy needed to get an object out of a rut or out of a hole and back to the 0 energy state where it has no potential energy at all. So that negative 196 joules communicates that you need exactly 196 joules just to get this object back up to the 0 energy state where nothing's affecting it. I'm going to draw a comparison now between electrons that are just floating in free space unattached to an atom and a bowling ball just sitting on the ground at a height of 0. Here, because the electron isn't attached to an atom, we would say that the electron is just moving freely in space and has no potential energy, similar to how the bowling ball could just be rolling on the ground with no potential energy. I'm going to imagine now that this electron gets close to an atom, and you'll notice that I've added a few levels of negative energy to this atom. The electron encountering this atom is kind of like the bowling ball encountering a hole in the ground that looks something like this, with different levels of negative energy that the bowling ball can fall down. Right now, the electron is not in the atom, and in a similar way, the bowling ball is not in the hole. I'm going to bring them both close to the edge of the atom and the hole. Here, the electron is still free from the nucleus of the atom and is not affected by it. It requires 0 electron volts to escape the atom. In a similar way, the bowling ball is still free from the hole. It still has an energy of 0 joules, which means it's not actually in the hole yet. So both of these things are kind of at the boundary of these different energy levels, but haven't fallen into negative energy yet. If the electron gets closer to the nucleus, though, if it goes down into that negative 1.6 electron volt level, suddenly the electron is stuck orbiting the atom, and it would need 1.6 electron volts added to it to escape the atom. So this is exactly like the bowling ball falling into that first level of the hole, and suddenly the bowling ball would need 1.6 joules of energy to escape the hole. So that's what these negative energies of the atom and the hole mean. There's another comparison between these where they're both being held there by a force. The electron is being attracted to the atom by the electrostatic force, and the bowling ball is being prevented from leaving by the force of gravity. If no energy is added to these objects, the bowling ball is just going to remain in that hole, and the electron is going to remain in orbit at that level around the nucleus. So the energy that an electron has in an atom is always recorded as negative because it's telling you exactly how much energy is required to escape the atom. We can imagine the electron drops more and the bowling ball drops more. So here the electron would need 2.5 electron volts to escape the atom. And you can see the bowling ball would now require 2.5 joules to escape the hole. And here the electron would require 3.9 electron volts to escape the atom, just like the bowling ball would require 3.9 joules to escape the hole. So that is what these negative energies are communicating to you, and so we always record electron energy levels as negative in an atom. It's a way of recording that the electron is stuck in the atom and requires that much energy to escape. We can now cover some basic vocab for electron energy levels. First of all, an electron energy level itself, or an energy state, is an amount of negative energy any electron can have in an atom. So as an example, I would say that there are 3 energy levels in this atom. The ground level or ground state of an electron is the largest magnitude of negative energy an electron can have in an atom. Here I would say that the ground state of this atom is negative 3.9 electron volts. That's the lowest possible energy the electron can have, the farthest it can be from zero in the negative direction. We say an electron is excited when it is not in the ground state. Excited is also used as a verb to mean moving up energy levels. So as an example, if the electron went from the negative 3.9 to the negative 2.5 energy level, we could say something like it was excited to the second energy level. There are also 2 variables that I need to introduce. The letter n is the number of the energy level. The ground level is always called n equals 1, the next level up is always n equals 2, and so on. So this is how I would label that here. I know that negative 3.9 electron volts is my ground level, and as I go up, these are the other energy levels of the atom. E subscript n is the value of the energy at energy level n. So here I would say that E1 is negative 3.9 electron volts, E2 is negative 2.5, and E3 is negative 1.6. As a note, we normally don't call 0 electron volts an energy level of an atom because by the time an electron is there, it's no longer in the atom. I'll talk about this a little bit more at the very end of the video. A really fundamental fact about electrons and atoms is that electrons cannot exist between energy levels in an atom. We say that the energy of an electron is quantized because it can only exist in certain specific quantities and not between those quantities in the atom. So as an example, here the electron is existing at an energy of negative 3.9 electron volts, and that's okay because that's one of the energy levels of the atom. It could also exist here at negative 2.5 electron volts, but there's no physical way for it to exist anywhere between those energy levels. So if I tried to say that this electron had an energy of negative 3 electron volts, that would not work. That would not be physically possible because that's between energy levels of the atom. So we say that the energy levels of an electron are quantized because they can only come in very specific quantities. This idea of quantized energy is going to be important for the rest of this topic. Electrons cannot exist between specific energy levels in an atom. There's a limited number of values of energies they can have when they're in the atom. Because we don't want to physically draw a picture of every complete atom, to represent electron energy levels, we draw horizontal lines separated vertically by distance proportional to the energy difference between them, with the ground state on the bottom. As an example, this is one way I could represent this atom using a simpler diagram. This is the type of diagram that we usually use in these problems. You can see that the ground state is on the bottom, the other energy levels are above the ground state, and the distance between the lines is proportional to the difference between the energies. So the difference between negative 3.9 and negative 2.5 is 1.4, and 1.4 is larger than that other difference of 0.9 electron volts. So I drew line 1 and 2 farther away from each other than line 2 and 3 to represent that the energy difference between the first two is bigger than the second two. We're now ready to learn about the relationship between photons and electrons. So energy is conserved. This means it cannot be created or destroyed, which means that if an object loses energy, that energy has to go somewhere. It can't just disappear into nothingness. If an object gains energy, that energy also has to come from somewhere. And we know from a previous lecture, which I've linked in the description, that photons carry energy. So this is the relationship between photons and electrons. Whenever an electron loses energy, a photon is created with the exact amount of energy that the electron lost. Whenever an electron gains energy, a photon with that amount of energy is absorbed or destroyed by the atom. What this is telling us is that if this electron with an energy of negative 1.6 electron volts were to drop to an energy of negative 3.9 electron volts, I can see that the change in energy there is negative 2.3 electron volts. The electron would lose 2.3 electron volts of energy, but that energy has to go somewhere. It can't just disappear. And so if the electron is losing 2.3 electron volts, that means that as it does that, a photon is going to be created with exactly 2.3 electron volts of energy, and the photon leaves the atom and goes off in a random direction. So every single time an electron loses energy, that energy leaves the atom as a photon. The only way for the electron to gain energy, as an example, if we want to move it from negative 3.9 eV to negative 2.5 eV, I can see that the difference between those energies is positive 1.4 electron volts. So that energy can't just magically appear, it needs to come from a photon specifically, and it needs to come from a photon carrying 1.4 electron volts of energy. If a photon impacts this atom with that exact amount of energy, the atom will absorb it, and the electron will move up that energy level. If a photon does not have the exact energy required to get an electron to a different energy level, it passes through the atom because the electron cannot exist between energy levels. For example, if a photon impacted this atom carrying 0.5 electron volts, right now our electron is at negative 2.5 electron volts of energy. That additional 0.5 electron volts would be enough to get it to negative 2 electron volts, which exists between energy levels. And we know that the electron cannot exist between energy levels, that's not allowed. What that means is that the photon will not be absorbed by the atom because if it were absorbed, the electron would do something that's impossible. What happens instead is that the photon just passes right through the atom and continues moving. That's going to be another really fundamental concept that we'll come back to a lot in this topic. Because electron energy is quantized, the electron can only be at specific energy levels, there are a limited number of energy changes an electron in an atom can go through. Because every change in energy emits or absorbs a photon, there are a limited number of photons which can be emitted or absorbed. So every energy change involves a photon with that same amount of energy, and there are a limited number of energy changes that can happen, so there are a limited number of photons that can interact with this atom. We can find each possible photon's energy using the electron energy levels. Normally when we do these problems, we're given energy levels that don't include the zero energy level, so I'm going to ignore that for now. And I'm going to use this chart to understand all the different ways an electron's energy can change in this atom. I'm going to start by finding the possible energies of photons that this atom could emit specifically. I'll worry about absorbing photons later. When an electron emits a photon, that's when it's moving down in energy level. So I just need to find all the different ways that an electron could move down in energy level in this atom. I can see as an example that it could follow this path where it drops negative 0.9 electron volts. If it follows that path, a photon of 0.9 electron volts is created, so that's one of the possibly emitted photons from this atom. The electron could also follow this path and drop 1.4 electron volts, which would mean that a photon would be created of 1.4 electron volts. So that's another possible emitted photon from this atom. There's one more possible path this electron could take where it drops straight from the third level to the first level. If it took this path, I can see that the energy change would be negative 2.3 electron volts. So that would mean a photon of 2.3 electron volts would be emitted. These are the only possible ways that the energy of an electron can change in this atom. There are no other paths it can take because it can't exist between energy levels. It has to end at one of the energy levels. So these are the only ways that an electron can lose energy if it exists in this atom. And so my list of possible energies of emitted photons are the only possible photons that can be emitted by this atom. This atom can only emit a 0.9, a 1.4, and a 2.3 electron volt photon, and no other energies of photons can be emitted. We can now think about which photons could possibly be absorbed by this atom. Those would be the energy changes of an electron as it went up in energy, because photons being absorbed add energy to the electron. And if you think about it, the possible ways that an electron can gain energy here are actually just going to be the reverse of the possible ways that it can lose energy. If I change the direction of all of these paths to go up in energy instead of down, I can see that the possible energy gains by the electron are the exact same as the possible energy losses by the electron. So this means that the possible energies of emitted photons always equal the possible energies of absorbed photons, because there are only three ways this electron can gain energy, and each one is the exact same amount of energy that it can emit. If I want my electron to gain 2.3 electron volts, it would have to absorb a photon of 2.3 electron volts, which is one of the three possible emitted photons. And if I wanted to gain 1.4 electron volts, it would have to absorb a photon of 1.4 electron volts, which is another emitted photon. And if I wanted it to gain 0.9 electron volts, it would have to absorb a photon of 0.9 electron volts. So this will always be true. The possible energies of emitted photons in an atom are always equal to the possible energies of absorbed photons. The last thing to know before we start doing example problems is that we can use an electron energy level diagram to find all possible energies of emitted and absorbed photons. Because we can use a photon's energy to find its wavelength and frequency, this is something I talked about in the previous lecture, which I've linked in the description. We can also find all the possible wavelengths and frequencies of the emitted and absorbed photons. I'll give you an example of doing that here. I can see I have 4 energy levels. That axis on the left is just telling me that's measuring energy in electron volts. And I can find either all the ways that an electron can emit or absorb a photon. I'll find all the ways that it can emit a photon, which means going down in energy. So I just need to use this chart to find all the different ways that an electron could lose energy in this atom. The first way would just be going from the highest to the lowest energy like this. And I can see that that energy difference is negative 12.75 electron volts. So if an electron did that, it would produce a photon of 12.75 electron volts. So that's the first possible photon that could be emitted. This is another energy change that could happen. I can see that's 1.55 electron volts. So I can just keep going through and finding every possible drop in energy that can occur on this chart and record the energy change for each one, and that's going to be the energy of an emitted photon. There's one here, and here, and here. Those are all the possible energy drops. So that means there are 6 possible energies of photons that this atom can emit, and I just found all of them and listed them on this table. I can use these energies to find the frequency of each photon using the equation for frequency and energy of photons. Energy equals Planck's constant times frequency. If I rearrange for frequency, I get this. And then I just need to plug in my numbers, remembering that I need to convert from electron volts to joules. So when I do that and plug in energy, I get a frequency for that first photon of 3.08 times 10 to the 15th hertz. And I can follow the same process for the others. If you have the frequencies already, there are actually 2 ways you can find the wavelengths of photons. You can either use the wavelength equation that uses the Planck constant, and if you did that, you would get this value. You can also use the fact that the speed of light is equal to its wavelength times frequency, so since you already have the frequency, you could also just divide the speed of light times the frequency to find the wavelength. So that would be the wavelength of the first photon, and these are the other wavelengths. So this is cool. I'm now able to find the wavelength and frequencies of light that will be emitted by an atom. These are all the possible wavelengths and frequencies of light that the atom will emit based on its specific energy levels. Finding these wavelengths and frequencies will be extremely important in the next lecture when we cover the absorption and emission spectra of atoms. Example number 2 asks 2 questions: a change between which 2 energy levels will emit a photon with the smallest possible wavelength, and which change will absorb a photon with the smallest possible frequency. You'll notice here that the energy levels are not written as numbers. It's just variables E1, E2, E3, and E4. So we can't just find all the wavelengths and frequencies and get the answer. We need another way of understanding this. In the lecture on photons that I've linked in the description, I talked about how the smaller the wavelength of a photon, the more energy it carries. So if I'm trying to find a photon with the smallest possible wavelength, that means I'm trying to find the photon with the largest possible energy that I can get from this atom. So I'm looking for the greatest possible energy change on this chart. And because the photon is being emitted, I'm looking for the greatest possible energy change down the energy levels. So if I want a photon with the smallest possible wavelength, it also has to have the greatest possible energy. So I'm looking for the greatest possible energy change down on this chart, which, if I think about it, would have to be here. There's no larger change in energy that can happen between these levels than going from E4 down to E1. And I know it's going down because we're emitting a photon, so the energy change that will produce the smallest possible wavelength is going from E4 to E1. That would be the answer to that first question. If we're looking for the smallest possible frequency, I remember from the photon lecture that the smaller the frequency, the smaller the energy. So I'm now looking for the smallest possible energy change that can happen on this chart. And I remember that the spaces between the horizontal lines tell me how large or small the energy change is. The larger the space, the larger the change. So if I'm looking for the smallest possible energy change, I'm looking for the smallest possible space between 2 lines. And because the photon is being absorbed, the electron will have to go up in energy, so that would be here. That's the smallest possible space between 2 lines on this chart. Going from energy level 3 to 4 will produce a photon with the smallest possible frequency that can be emitted by this atom. Example number 3 says a photon with energy of 2.1 electron volts is absorbed by this atom and excites an electron. The electron will move between which 2 energy levels? So I basically just need to look around at this chart and see if I can find which 2 lines have a difference of exactly 2.1 electron volts between them. And if I look around for that difference, I eventually find that it exists between 2.5 and 0.4. So that's where the electron would change by exactly positive 2.1 electron volts. So the answer to this would be moving from negative 2.5 electron volts to negative 0.4 electron volts, or between the second and fourth energy levels. There are times when you'll have to calculate the energy states of an atom using an equation. As an example, the equation for the energy levels of hydrogen atoms is E subscript n is equal to negative 13.6 over n squared electron volts. What is the wavelength of a photon required to excite an electron from the ground state to n equals 3? So to know the wavelength, I need the energy, and to know the energy change, I need to know the difference between the ground state and the third level. So I need to know what those energies are. I know that the ground state is just a code word for n equals 1. So to find the energy there, I just plug in 1 into n, and I find negative 13.6 electron volts. So that's the energy of the ground state. And the energy at the third level, I just plug in 3 into n, and I get an answer of negative 1.5 electron volts. If an electron is excited from the ground state to the third state, I can see that the change in energy is going to be positive 12.1 volts. So that's the required energy of a photon that needs to be absorbed to make that happen. So I now have all the information I need to solve for the wavelength of the photon, and I know that the energy is 12.1 electron volts. I just need to convert that to joules, and when I do that, I find it's 1.94 times 10 to the negative 18th joules. So I plug that into my equation and get a final wavelength of 1.03 times 10 to the negative 7th meters. So if I send a photon with that exact wavelength to impact the atom, the photon will be absorbed and excite an electron from the ground state to the third energy level. These are just a few extra notes before we go. IB doesn't cover these specifically, but they still might be useful to know. The energy levels of an electron always get closer together as they increase. You may have noticed that pattern throughout the video. Real atoms actually have infinite energy levels that get closer and closer and closer to zero. So they kind of asymptotically approach 0 electron volts. And there's always an infinite number of them as they get closer and closer to 0. So we sometimes refer to the 0 electron volt line as n equals infinity. It's the infinitieth possible energy level because there's always an infinite number of energy levels leading up to it. But in most idealized problems, we only worry about a few energy levels at a time. The very last thing to know is that all atoms of the same element have the exact same values for their energy levels. This will be really important in the next lecture on absorption and emission spectra. As an example, the energy levels of all hydrogen atoms follow this formula. The energy is equal to negative 13.6 over n squared electron volts. So that is everything that you need to know about the relationship between electron energy levels and photons.